Welcome to this coding problem walkthrough. Today, we'll explore problem number 169, majority element. We'll break down the problem, discuss possible approaches, and analyze their time and space complexities. Let's dive in and solve this step by step. The problem we are solving is to find the majority element in a given array. A majority element is defined as the element that appears more than n/2 times, where n is the size of the array. Your task is to write a function that takes in this array and returns the majority element. It's important to note that the problem guarantees the majority element will always exist in the input array. For the input, you are given a single integer array called nums of size n. The output will be a single integer, which represents the majority element. Now, let's look at some examples to better understand the problem. In the first example, the input array is 3, 2, 3. The array has 3 elements, and the number 3 appears twice. Since this count is greater than 3/2, which equals 1, the majority element is 3. For the second example, the input array is 2, 2, 1, 1, 1, 2, 2. Here, the array contains 7 elements, and the number 2 appears 4 times. This is greater than 7/2, which equals 3. So the majority element is 2. Let's consider another example. If the input array is 1, it contains just one element. Since 1 is the only element in the array, it is trivially the majority element. Moving on to the constraints, the size of the array n is defined as the length of nums, and it can range from 1 to 50,000. The values in the array nums I can range between -10 to the power of 9 and 10 to the power of 9. Additionally, the problem guarantees that the majority element will always exist in the array, which simplifies the task because you don't have to handle cases where no majority element is present. Now, let's talk about some edge cases you might encounter. First, if the array contains only a single element, like 5, that element is automatically the majority element. Second, if all elements in the array are the same, such as 7, 7, 7, 7, the single unique value, 7, will clearly be the majority element. Lastly, consider an array where the majority element appears exactly half the time plus 1, like 4, 4, 4, 2, 2, 4, 2. Here, the number 4 appears 4 times, which is more than half the size of the array, 7/2, which equals 3. These cases illustrate the diverse scenarios your function should handle while maintaining efficiency. To solve the majority element problem, we can consider several approaches. The first is the brute force method. Here, the intuition is straightforward. We count the frequency of each element in the array and determine if any element appears more than n/2 times. To implement this, we use nested loops, where the outer loop picks each element, and the inner loop counts its occurrences. If any element's count exceeds n/2, we return it as the majority element. While simple, this approach has a time complexity of n², due to the nested loops, which makes it inefficient for larger arrays. Additionally, it uses no extra space, giving it an O(1) space complexity. However, the inefficiency of its time complexity is a significant drawback, especially for larger datasets. Another method we can consider is the hash map approach. By using a hash map, we can count the occurrences of each element in a single traversal of the array. As we traverse, we store the counts in the hash map, and at the end, we can determine which element has a count greater than n/2. This method is a more efficient alternative to brute force, as it avoids nested loops and reduces the time complexity to O(n). The hash map approach, while faster than brute force, comes with its own trade-offs. Specifically, it requires additional space to store the hash map, resulting in an O(n) space complexity. This can be a concern in memory-constrained environments where minimizing space usage is critical. Another approach we can consider is sorting. The intuition here is that if the majority element appears more than n/2 times, it will always occupy the middle position in a sorted array. To implement this, we sort the array and then simply return the element at the middle index. This approach has a time complexity of O(n log n) due to the sorting step, and it can be space efficient with an in-place sorting algorithm, giving it an O(1) space complexity. However, sorting the entire array can be unnecessary when we're only interested in the majority element, making this method less optimal than linear time solutions. While both the hash map and sorting approaches improve upon brute force, they still leave room for further optimization in either time or space complexity. The Boyer-Moore voting algorithm provides a highly efficient solution to the majority element problem. This algorithm leverages the problem's constraints, specifically the guarantee that a majority element always exists. The key idea is to pair off different elements, ensuring that the majority element remains unpaired and dominates the count. To implement this, we maintain a candidate variable and a counter. As we traverse the array, we set the current element as the candidate if the counter is 0. If the candidate matches the current element, we increment the counter, otherwise, we decrement it. By the end of the traversal, the remaining candidate is the majority element. This approach achieves a time complexity of O(n), due to the single traversal and a space complexity of O(1), as no extra data structures are used. However, one limitation of this algorithm is that it assumes the input always contains a majority element. In cases where this guarantee is absent, additional verification would be necessary to confirm the result. Despite this, the algorithm's efficiency in both time and space makes it a compelling choice for this problem. The Boyer-Moore voting algorithm stands out as the optimal strategy for solving this problem due to its linear time complexity and constant space usage. Unlike the brute force approach, it avoids the inefficiency of quadratic runtime. Compared to the hash map approach, it eliminates the need for extra space. While sorting is a viable option, it is slower than Boyer-Moore's linear time performance. This algorithm capitalizes on the guarantee of a majority element, using the pairing-off technique to cancel out non-majority elements. One key observation is that the majority element will always dominate the count after all opposing elements are paired off. This elegant mechanism ensures that the majority element emerges as the last candidate. However, the trade-offs include its reliance on the guarantee of a majority element. If this guarantee is absent, additional steps would be required to verify the result. Compared to the hash map approach, Boyer-Moore is slightly harder to implement, but its superior space efficiency makes it the most practical and optimal solution. In conclusion, this algorithm is the best choice for tackling the majority element problem efficiently and effectively. To solve the majority element problem, we need to identify an element in an array that appears more than n/2 times, where n represents the size of the array. One straightforward way to approach this is by using a brute force method. This involves iterating through the array element by element. For each element, we count how many times it appears in the array and then check if it satisfies the majority condition. Specifically, for each selected element, we initialize a counter to 0. Then, using a second loop, we compare the selected element to every other element in the array, incrementing the counter whenever there's a match. Once we know how many times the element appears, we check if this count exceeds n/2. If it does, we can immediately return this element as the majority. This process ensures that every potential candidate is checked thoroughly. If no majority element is found for a given candidate in the current iteration, we simply proceed to the next element in the array and repeat the process. It's important to consider edge cases when implementing this approach. For example, if the array is empty, the algorithm should return a value indicating that no majority element exists, such as -1 or null. Similarly, if no element meets the majority condition in the entire array, we must ensure the algorithm correctly signals this outcome. The process terminates when the outer loop has iterated through all elements without finding a majority. By walking through an example, such as the array 3, 3, 4, 2, 4, 4, 2, 4, 4, we can observe how the algorithm systematically evaluates each candidate element to identify the majority if it exists. For instance, starting with the first element, 3, the outer loop selects this as the candidate. The inner loop then counts how many times 3 appears in the array, which is 2. Comparing this count to the threshold n/2, which is 4.5 in this case, we see that 2 is less than 4.5, so 3 is not the majority. The process continues with the next candidate, 4. The inner loop counts the occurrences of 4, which is 5. Since 5 is greater than 4.5, 4 meets the majority condition, and the algorithm returns it as the result. This example highlights the inefficiency of the brute force approach. With a time complexity of O(n²), the nested loops result in redundant comparisons and repeated processing of elements, even after their majority status has already been determined. Optimizing this approach could significantly reduce computational overhead. For instance, data structures like hash maps or algorithms like the Boyer-Moore voting algorithm provide more efficient alternatives. Breaking down the key operations, the outer loop iterates over all elements in the array, and for each iteration, the inner loop performs another pass to count occurrences, leading to a combined time complexity of O(n squared). To optimize this, we can use a hash map to count occurrences in a single pass, reducing the complexity to O(n). Alternatively, the Boyer-Moore voting algorithm achieves the same time complexity of O(n), while using only O(1) additional space, making it an even more efficient option. It's also important to address edge cases. For example, if the array is empty, the algorithm should handle this gracefully by returning null or -1. If no majority element exists, the result should reflect this outcome. Arrays where all elements are the same or contain only one element are straightforward, as the single element is trivially the majority. Lastly, handling edge cases like negative numbers or mixed data types requires validating the input to ensure proper functionality. These considerations help ensure the algorithm is robust and efficient in all scenarios. The problem requires finding the majority element in an array, which is defined as an element that appears more than n/2 times, where n is the size of the array. The Boyer-Moore voting algorithm efficiently solves this problem in O(n) time and O(1) space. ###explanation. 1. Initialization. We initialize candidate as none and count as 0. The candidate variable will eventually hold the majority element, while count keeps track of the balance of occurrences. 2. First pass, finding the candidate. As we iterate over the array, we check the count variable. If count is 0, we assign the current element, number, as the new candidate. For every element, we update the count. If the current number matches the candidate, we increase the count by 1. Otherwise, we decrease it by 1. This step effectively balances out non-majority elements, ensuring that the majority element remains as the candidate. 3. Second pass, optional verification. While the problem guarantees the existence of a majority element, we would typically verify the candidate by counting its occurrences in the array to ensure it appears more than n/2 times. However, since the problem guarantees its existence, we can skip this verification step. ### complexity. Time complexity, the algorithm completes in O(n) time because it iterates through the array once. Space complexity, the algorithm uses O(1) space as no additional data structures are used. In summary, this concise approach leverages the Boyer-Moore voting algorithm to identify the majority element in an efficient and elegant manner. This is a Java implementation of the Boyer-Moore voting algorithm for determining the majority element in an array, mirroring the provided Python solution. The code uses a single pass to identify the majority element with O(n) time complexity and O(1) space complexity. Key differences include Java-specific syntax, such as type declarations and enhanced for loops for iterating through arrays. The implementation guarantees correctness due to the problem constraints ensuring a majority element exists. Here, we're solving the problem using the Boyer-Moore voting algorithm, which is designed to find the majority element in an array. The majority element is defined as the number that appears more than n/2 times in the input. Starting with the initialization, we set candidate to none and count to 0. Next, we iterate through the array. For the first number, 3, since the count is 0, we set the candidate to 3 and increment the count to 1. Moving to the second number, 2, it's different from the current candidate, so we decrement the count back to 0. For the third number, 3, because the count is 0 again, we reset the candidate to 3 and increment the count to 1. After iterating through all the numbers, the candidate remains 3 with a count of 1. Finally, the candidate, which is 3, is returned as the majority element. In this example, we use the same algorithm on the input, 2, 2, 1, 1, 1, 2, 2. We begin with the initialization, candidate is set to none and count to 0. As we iterate, the first number is 2. Since the count is 0, we set the candidate to 2 and increment the count to 1. The second number is also 2, which matches the candidate, so we increase the count to 2. The third number is 1, which is different from the candidate, so we decrease the count to 1. For the fourth number, 1, it still doesn't match the candidate, so the count drops to 0. At this point, when the fifth number, 1, is processed, the count is 0, so we reset the candidate to 1 and increment the count to 1. The sixth number, 2, doesn't match, so the count is decrement to 0. Finally, the seventh number, 2, resets the candidate back to 2 and the count increases to 1. By the end of the iteration, the candidate is 2 with a count of 1. After iterating through all the numbers in the array, the final state is candidate equals 2 and count equals 1. Therefore, the algorithm returns 2 as the majority element. Now, let's examine another example with the input 1, 1, 1, 2, 3, 1, 4, 1, 1. As always, we start with the initialization, candidate is set to none and count to 0. From here, we'll process each number in the array step by step to determine the majority element. Starting the iteration, the first number is 1. With the count at 0, we set the candidate to 1 and increment the count to 1. The second number is also 1, which matches the candidate, so the count increases to 2. The third number is another 1, still matching the candidate, so the count goes up to 3. The fourth number is 2, which is different from the candidate, so the count is decrement to 2. The fifth number is 3, again not matching the candidate, so the count decreases to 1. For the sixth number, 1, it matches the candidate, so the count increases to 2. The seventh number, 4, doesn't match, so the count is decrement to 1. The eighth number is 1, which matches the candidate, so the count increases to 2. Finally, the ninth number is another 1, matching the candidate once more, and the count increases to 3. At the end of the iteration, the candidate is 1 with a count of 3. After processing the entire array, the final state is candidate equals 1 and count equals 3. The algorithm then returns the candidate, which is 1, as the majority element. This demonstrates how the Boyer-Moore voting algorithm efficiently identifies the majority element by maintaining a single candidate and adjusting the count dynamically as we traverse the array. The time complexity of the Boyer-Moore voting algorithm is O, n, where n is the length of the input array nums. Let's break this down. During the first pass, the algorithm iterates over the array exactly once to determine the majority candidate. For each element, it either updates the candidate variable or adjusts the count variable, both of which are constant time operations. Since we process each element only once, the total time for this step is O, n. Now, while a second pass through the array could be used to verify the candidate, this isn't required here because the problem guarantees the existence of a majority element. Without the verification step, the overall time complexity remains O, n, as there's only one complete iteration of the array involved. Now, let's consider the best, average, and worst-case scenarios. In all these cases, the time complexity remains O, n. This is because the algorithm always performs one complete pass through the array, regardless of the distribution of elements. Mathematically, we can see this by examining the operations on each element. Each is processed in constant time, and since there are n elements in the array, the total number of operations is proportional to n. That gives us O, n, as the overall complexity. This uniformity across all scenarios highlights the efficiency of the algorithm. Moving on to space complexity, the Boyer-Moore voting algorithm is highly space efficient, with a space complexity of O, 1. This is because the algorithm only uses two auxiliary variables, candidate to store the current majority candidate and count to track the balance. Both of these variables occupy constant space, irrespective of the size of the input array. Importantly, no additional data structures, such as arrays or hash maps, are used in this approach. With such minimal memory usage, the algorithm is exceptionally space efficient, making it a standout solution for this problem. Finally, let's compare the Boyer-Moore voting algorithm to other approaches. In terms of time complexity, it matches the efficiency of the hash map approach at O, n, but significantly outperforms the brute force method, which runs in O, n squared. However, the real advantage lies in space complexity. The Boyer-Moore algorithm uses only O, 1, space, while the hash map approach requires O, n, space to store frequency counts. The brute force method also uses O1 space but at the cost of much lower time efficiency. Overall, the Boyer-Moore voting algorithm achieves the optimal balance of O and time and O1 space, making it the most efficient solution among the three. When solving the majority element problem, there are several common mistakes to watch out for. First, failing to account for edge cases, such as empty arrays or arrays with only one element, can lead to runtime errors. A simple fix is to handle these cases explicitly at the start of your code. Next, inefficient use of data structures, like using a dictionary for counting when a more efficient algorithm like Boyer-Moore could suffice, can unnecessarily increase both memory usage and runtime. Choosing the optimal approach is key here. Another mistake is assuming all inputs are valid. If you overlook the problem constraints and fail to confirm whether the array guarantees a majority element, your code might produce incorrect results. Carefully reading the problem description can help prevent this. Lastly, misunderstanding the definition of the majority element, confusing more than n/2 times with exactly n/2 times, can lead to errors in logic. Revisiting the definition ensures your solution aligns with the problem requirements. Now, let's consider performance limitations. For large inputs, such as arrays with n equal to 10 to the power of 5, using a brute force solution is not practical and will likely result in time limit exceeded errors. To address this, you need to optimize your solution to meet the required time complexity, for example, using the Boyer-Moore voting algorithm, which runs in O(n) time. This brings us to its importance in interviews. Majority element problems often test your ability to recognize patterns, such as counting frequencies or applying greedy algorithms to identify dominant elements. In most interviews, you should aim to propose the Boyer-Moore algorithm as it is both efficient and elegant, running in O(n) time with O1 space. However, you should also be prepared to explain why it works, specifically, how it cancels out non-majority elements, and discuss any trade-offs, such as the need for a second pass to confirm the result. Finally, always account for edge cases, like arrays that might lack a majority element if the problem constraints don't guarantee one. There are also related problems that build on the concepts in majority element and can help reinforce your understanding. For example, LeetCode 229, Majority Element 2, is a variation that requires finding elements appearing more than n/3 times, which introduces additional complexity. LeetCode 136, Single Number, shifts focus to finding a unique element using XOR operations, which is another efficient approach for array manipulation. LeetCode 128, Longest Consecutive Sequence, tests your ability to handle array manipulation using hash-based solutions. And of course, LeetCode 169, the original majority element problem, serves as a foundation for all these variations. Exploring these problems helps you recognize patterns and develop strategies for solving a wide range of similar challenges. Finally, let's consider some alternative approaches to solving the majority element problem. One common method is using a hash map to count the frequency of each element. This approach runs in O(n) time but requires O(n) space. While it's simple to implement, the extra space usage can be a drawback. Another approach is sorting the array. Once sorted, the majority element will always be located at the middle index. This method is intuitive and uses O(1) space, but its O(n) log n) time complexity makes it slower than other options. The optimal approach is the Boyer-Moore voting algorithm, which uses a greedy strategy to cancel out non-majority elements in O(n) time and O(1) space. While this method is the most efficient, it may require you to explain why it works, especially in an interview setting. Each of these approaches has its trade-offs, and understanding them will help you select the right one based on the problem constraints and requirements. Great job making it to the end. To summarize, we tackled the majority element problem using efficient approaches and analyzed their complexities. Keep practicing similar problems to strengthen your skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!